Hi everyone, my name is Charles Lin, and today I'll be presenting our work on analyzing economic incentives in serverless. This is work from myself, Joey Gonzalez, and Joe Hellerstein from the RISE lab at UC Berkeley. The definition of serverless that we'll explore in this paper is not any particular product or offering, but rather the general idea of paying for consumption instead of capacity. Our goal is to understand in broad strokes when is serverless advantageous, when will this consumption over capacity idea succeed in the long run. So why this economic angle? Well, we know serverless is exciting, it's on the rise and we're seeing increasing adoption. But despite that, it's still in its relative infancy. Provision servers today are far from being replaced. And we may also expect that servers will never entirely be replaced. So the needle will fall eventually somewhere in the middle, but where will it fall exactly, and what are the factors that will influence that outcome? So what we want to do is to be able to inform research and build intuition for this problem. We know most of the problems with serverless, and we know that there are many solutions being explored. We want to understand which parts of the design space are economically sensible, which directions have the most transformative potential. To be concrete, here are a couple of things that we want to be able to reason about that the model might help us with. So one is gauging how compelling arbitrary improvements are. Suppose there's some new research that shows some technique can reduce strike-through latency by 2x for some serverless application, which we'll call Y. That's good to hear, of course, but what does that mean for the big picture? Is it game-changing? What order bit is being flipped by this technique? Are we enabling the previously infeasible, or is it an incremental improvement? And not only that, what if cloud vendors change serverless prices in the future? Or quite likely, they'll change the characteristics of their products, add new products. We don't want to have to redo our benchmarks, but instead we want to intuitively reason about whether application Y on serverless makes sense for some fundamental reason or only temporarily. And the other thing is we want to inform design decisions for serverless. So what we were working on that led to this line of work was actually auto-scaling policies and pricing quality of service. We wanted to design contracts that made sense for both the customer and the provider. But we could come up with a contract and analyze it, but we had difficulty understanding whether such a contract would make sense in the long term, if it was optimal for some definition of optimal. And that's why we started looking into serverless incentives. So none of what I'm about to present in this work is particularly complex or difficult, but our hope is that it gets people viewing serverless not as some particular product or black box artifact that exists in time. Instead, we want to view it as a conscious consumption versus capacity trade-off that we can analyze. So now we'll look at developing this model. The constraint we begin with is that for any serverless product to be viable, both the provider and the customer must prefer it to a serverless option. Now, prefer can mean many things. There are many different factors that can influence this decision. In our paper, we chose some factors which we thought are necessary conditions, but we make no claims as to their sufficiency. For the provider, we assume profit to be the most important condition. So the service product should bring in at least as much revenue as if the resources were spent on a serverless product instead. To do this, we consider the utilization ratio and the price ratio for any particular vendor and product. And this expression simply says that resource underutilization from serverless must be compensated for by a higher product price. The customer also faces an analogous price to utilization trade-off, which is that the premium they pay for serverless must be worth the quote-unquote time that they would waste if they had provisioned a serverless product instead. The idea here being that the whole point of serverless existing is that customers are unable to provision with perfect granularity. However, price isn't the full story for serverless customers today. Another important decision factor is that they might just find the current service offerings less useful. So perhaps they might have requirements for specialized hardware that just isn't found on serverless platforms today. Or they might have quality of service demands like latency. And then there's other concerns like amortized transition costs, operational concerns, or locking concerns. We can model usefulness as a binary variable, 1 or 0 for useful or not, but we might as well make it continuous. And in our model, it's represented as VS over VR, the relative usefulness of the serverless product over the serverfull option. Now, to be clear, we're not saying that we can find exact values for these terms, but we do consider it to be a necessary condition, and thus it should appear in our expression. Now, when we combine the conditions that we've established for the provider and customer, we get an expression that looks like this. And it's a relation between the characteristics of the provider and the customer about how much better providers are at using their resources than individual customers using their provision resources, and also about how useful serverless products are. Now, the price ratio term in the middle serves as a publicly known bound for these otherwise opaque terms. And for the rest of this talk, for brevity, we'll denote the 4 customer characteristic terms on the right side as alpha. The first thing we can do with this model is classify all the customers in the cloud computing market. Individual customers and their individual use cases can have different characteristics and thus different values for alpha, but we can still classify all of them into one of 3 categories. A customer can have alpha less than 1, which means that no amount of utilization or price improvements on the provider side will help them. For them to see serverless adoption, more useful serverless products are required. Then a customer can have alpha between 1 and C inverse. These customers prefer consumption-based versus capacity-based pricing if possible, but providers cannot yet profitably serve these customers. Finally, we have customers who have alpha values above C inverse, which means that providers are able to profitably provide serverless products to these customers. And if their alpha values are above the price ratio, then rationally they are already using serverless products. In addition to looking at the value of alpha for individual customers, we can increase the granularity further and look at the value of alpha for the individual resources that a customer is provisioning to accomplish some task, such as individual VMs. And by doing so, we can start to talk about the value of autoscaling. So pictured here is a straightforward simulation where a customer is provisioning to serve a generic job queue, and they are statically provisioning for peak. Now, since they're doing this, as they provision more and more resources, the marginal benefit of each resource goes down, and they more and more prefer a serverless autoscaling solution. Here we have 3 different job configurations. We have a random in blue, which is Poisson random inter-arrival time. And then we have a burstier workload, which has exponential inter-arrival time, and a predictable workload where the arrival time is close to constant. As you can see in the for the random job queue, the customer at first is fine with their provision resources, but after they've provisioned for around half peak, that's the break-even point where the customer begins preferring a serverless autoscaling solution. And you can see that this break-even point, as you would expect, happens even earlier for a burstier workload at around 1/4 of total resources provisioned. Now, statically provisioning for peak is, in essence, the worst, quote-unquote, a customer can do. So let's look at the other end of the spectrum. Realistically, how well can a customer manage its resources? So to do this, we'll look at the same simulation, but we've given the customer can now dynamically allocate and deallocate resources. And in addition, the customer has Oracle abilities in 1-minute windows. So for each 1-minute window, the customer knows ahead of time what the peak load will be. As you can expect, the customer's resource efficiency improves in this scheme, but surprisingly, it does not substantially change the break-even points at which the customer begins preferring serverless, which is around 1/2 of total resources provisioned for the Poisson random workload, and 1/4 still for the bursty exponential workload. And this is a simplistic, straightforward simulation, but the parameters that we're using for workloads are quite different, and yet the break-even points for preferring serverless change so little, even at the complete other end of the spectrum in this scheme. So this is surprising to us, and it suggests that there might be some sort of limitation as to how well a customer can both dynamically allocate resources and use them effectively. Lastly, we'll look at examining the value of quality of service. In the previous two scenarios, those were at opposite ends of the spectrum. Realistically, a customer is not going to be statically provisioning for peak, but they also won't be able to dynamically provision with such fine-grained accuracy as an Oracle. So they'll be somewhere in the middle, and sometimes they'll have to end up under provisioning. And when that happens, they'll incur some amount of queuing latency or other degradation in quality of service. Now, in this scenario, they could still have provisioned more resources, and that would have improved their quality of service. But each additional resource they provision is of less marginal value to the customer. So this chart shows the alpha of the last VM needed to reduce queuing latency below a percentile target. And I believe this is for the Poisson random workload from the previous scenario. And here we can see that to reduce, say, P95 queuing latency below 1 second, the last VM needed would need to have an alpha of about 10 to the 2, which is greater than the current serverless price ratio by a pretty wide margin. And this suggests that there can be significant value for customers even if modest quality of service guarantees were provided for serverless. In conclusion, here are some takeaways from our paper. First, serverless systems that are price competitive with serverful designs are sort of to be expected according to our model, and we will inevitably, hopefully, see many more of these in the future, especially as specialized hardware and other improvements enter serverless. One direction that we're particularly interested in is hybrid serverless designs, which explore a mix of provision capacity and pay for consumption. Our model suggests that a mix of these two might actually be cost optimal for a wide class of workloads and use cases. Finally, we should think consciously about incentives and trade-offs to consumers when designing policies for new serverless systems. Whether you're designing a new serverless application or infrastructural improvements to a serverless system, the trade-off is whether or not the consumer is able to accomplish the same thing on their own. And if the answer is yes, then that's okay. But if the answer is no, and you've accomplished something that the consumer can't accomplish on their own with provision resources, then that's a lot more compelling. Thank you for taking the time to listen to my talk. I do hope that you found it interesting. And if you have any questions or comments, we would love to receive them at the emails listed.